So let us continue. The one point I want to emphasize is about the how the low weight vectors in the dual play a good role. Okay, so I am not going to, once again it is a heuristic idea, but I want to emphasize that a little bit because it is important in what follows. We will use that later on. So if you have an so basically low weight vectors dual are important. Okay, so the reason why this is true is, if you have, let us say, if you just, this is again a heuristic justification, but it also is valid very much in practice. Okay, if you have x equals, let us say x1 XOR x2 XOR so on till xn, okay, and probability that xi equals 1, let us say is or xi equal to 0, okay, whatever, one of those two things, xi equal to 0 is let us say some p, okay, some p, and xi's are independent, say, okay. If you have a situation like this, one can actually exactly compute the probability that x is equal to 0, okay. So it will work out as something like 1 minus 2p raised to the power n by 2. Okay, so this is another way of writing that expression. This is it's quite easy to say. So as n becomes large, okay, whatever the value of p is, what is going to happen to this probability? Yeah, this tends to half as n tends to infinity. Of course, it is true. We are going to take p to be less than a half, for instance. Okay, then this works out. Okay, so maybe it is 2p minus 1. I don't know. I mean, one of those two expressions, depending on which is greater. This is greater than half, less than half, etc. Okay. So anyway, so this is the kind of expression you would get. So what I am trying to say is, suppose p is very low, like 0.01, okay, which means what? It means you know x1 through xn very precisely. Okay, well, I say very precisely, with very good confidence you know x1 through xn. Okay, probability that xi is 0 is 0.001, for instance. Okay, and you think you know that x1 is almost certain to be 1. Okay, you know that all these things, but even if in that case the extrinsic information that all these xi's are giving about x can become very bad. As in, what is very bad now? If this extrinsic information evaluates to half, then you might as well not use the extrinsic information. I mean, before that I can tell you is half. Okay, probability is half. Okay, so extrinsic information being half, probability being half is very bad. Likewise, likelihood ratio being 1 is very bad, and LLR being 0 is very bad. Okay, all these things are not very good informations. Okay, you do not have any good belief on that. Okay, so if n becomes very large, if n becomes 10 and 20 and all that, not 10, 20 maybe it's not too bad. If n becomes 100, 200, 300 and all that, then this equation is definitely going to go to half. There is no point in using those large weight equations. So once it goes to half, what does it mean? The log likelihood ratio from this extrinsic information is 0. Okay, so whether you add it or not, what will happen? The final expression you calculate, whether you add this or not, or worry about it or not, absolutely no difference it makes. Okay, so you might as well not worry about these large length, large weight vectors in the dual. Okay, those things you don't have to account for in your soft decoder. On the other hand, if there is a very low weight vector in the dual, then it will play a very big role, because it will give you very good probabilities. Okay, and those you have to account for. Okay, so this principle is exploited a lot in the soft decoders. In fact, even in the construction of codes, you will exploit this principle. You will try to have codes in which these low weight vectors in the dual can be very easily accessed. Okay, so you will see that is the principle of a very popular code called low density parity check code. Okay, so they use these kind of ideas. Okay, so this idea, while being heuristic, plays a big role in practice. So you should appreciate that. Okay, so hopefully this is clear. What happens when you XOR too many things? It goes away. So this is also crucial in your approximate decoder. Okay, so you know which term to throw away. The term corresponding to the large weight vectors in the dual are not important, okay, only the lower weight vectors play a big role. So as you go along, what you do later on does not really matter. I mean, initially you should take care of the low weight vectors very carefully. After that, the larger weight vectors, do whatever, you add, subtract, do not consider, it may not make a big difference to your final log likelihood ratio. Okay, all right. So hopefully this is clear. Okay, so one theme that I have been following on all along is this notion of suboptimal, okay, and this notion of things being very complex and complicated. Okay, so what will happen when you look at suboptimal implementations with very complex computations is analysis is pretty much impossible. Okay, so you cannot do precise analysis. Okay, so you have to have some engineering way of doing the analysis. Okay, so that engineering way of doing the analysis is this idea of simulating and finding the coding gain. Okay, so which is what I am going to describe now. Okay, simulations and coding, and to find, or let us say to find coding gain. Okay, I have not described what coding gain is, I will describe that soon enough, and then we will see how we can do simulations from just from a high level, how to do simulations to fix this coding gain. It is a very simple idea, but nevertheless it is important because in practice today codes have become so complicated. The only way to find do any analysis is to just simulate. Okay, and so you should know how to go about doing that. Okay, so that is why I think this is a good thing to emphasize. Okay, so first of all, what is coding gain? Okay, so to define that one needs to be a little bit more careful. Okay, so a little bit careful. You can't just say something is a coding gain and let it go. Okay, so the main idea here in coding gain is this notion of a energy per bit. Okay, this is an important idea, per information bit. Okay, so this helps in doing fair comparisons. Okay, so this is mainly for doing fair comparisons. Okay, I think I pointed this out once before when I was dealing with the repetition code. Okay, when you do not do any coding, all the energy you are spending is for information. Okay, you are not spending any energy for anything other than sending information, but when you do coding, you are going to send additional redundant parity bits which are not information. Okay, and you have to spend some energy there. Okay, and you have to account for that energy in any comparison. You can't just let it go. Okay, then it is not a fair comparison. Okay, so I will show you how to account for it in Bpsk over AWGN. It is quite easy to do even for other things also, but let us just do that because we are always looking at Bpsk AWGN. Okay, so in an uncoded Bpsk situation, what would you do? You would have one bit. Okay, Bpsk. Okay, you have one bit. Okay, 0 or 1, it goes to one symbol which is +1 or -1, then noise gets added to it, normal with 0 mean and variance sigma square, and you get one received value, right. So just one value and you make a decision. Okay, so if you talk about energy per information bit, which is usually called EB, okay, energy per information bit is basically, this is defined as the variance of the symbol here. Okay, so why is it the variance of the symbol? Basically it's the reason is you have to think of this as representing the symbol as representing a voltage. Okay, and then the square of the voltage becomes some kind of power if you normalize the resistance to 1 ohm or something. So that's actually true. See, when you take waveforms and then you define a basis and convert them into constellations, the energy in the waveform corresponds to the magnitude square of the vector, right. So if you remember your digital communications well, in the vector space representation of signals, the energy in the waveform, that is the integral x mod x of t squared, is the same as norm of the x. Okay, so now that is in terms of probability, if you think of this as some random variable x, that basically becomes expected value of x squared. Okay. So we will say x is usually uniformly distributed, plus 1 and minus 1 equally likely, okay, for a particular symbol. So this simply becomes 1 for Bpsk AWG. If it is not Bpsk AWG, you have to evaluate this expected value of x squared. Of course, I have assumed mean is 0. Okay, it's usually always good to keep mean 0. Mean is not 0, I have to account for that also. So that's why it's expected value of x squared. Okay, so I've said variance, but remember it's expected value of x squared. Assuming mean 0, that works out. Okay, so this is 1. Okay, EB in the uncoded case is 1. All right. So now noise power, we simply take it as noise energy, so to speak. Noise energy, we simply take it as sigma squared. Okay. All right. So the sigma squared, if you convert from white Gaussian noise through the correlator, etc., you will see this is the same as n naught by 2. Okay. So this n naught is some number that communication engineers will talk about. It's the height of the noise spectrum. Okay. So it's some number, and it depends on the temperature, etc. So you can put down some number for it. Okay. So the white noise that you expect in your receiver will be controlled by this n naught, and if you do your receiver right, if you do orthogonal projections or match filtering carefully, you will get a noise of n naught by 2. Okay, that's for the variance. Okay, so this is just some kind of digital communication. Once again, we do not have time to go into these details here. So I'm assuming you're doing either the course now or you've done it before and you know that this is true. Okay, so if you want to think of SNR for the uncoded case, a good SNR to have is basically energy per symbol. Okay, so this is the same as energy per symbol, right? Energy per information bit is the same as energy per symbol. Okay, so SNR is usually defined as ES by sigma squared. Okay, so if you want to convert to EB and N naught, this would work out to EB by N naught over 2. Okay, so this is a way to think about it, but usually SNR people will think of ES by sigma squared. Okay, so how will you simulate such a system? It's very easy, right? So if you for instance, if you are familiar with MATLAB, if you want to generate 1000 instances of this system, you are going to generate 1000 random bits, do 1 minus 2u, you get 1000 symbols, then generate 1000 numbers according to a pseudo random Gaussian distribution which MATLAB will give you, then have a pseudo power, add it, you will get so many received values. Okay, and what is the optimal decoder here? You have to just slice. Okay, so you slice and you get a estimate for the bit. Okay, right. So if you do that, so here in this case with the Bpsk we have assumed this simply becomes 1 by sigma squared. Okay, so let me just make sure I am not making any mistake here. It's okay. All right. So then the probability of error. Okay, I am having to go to the next page, but probability of error. So maybe we will keep half a page there and half a page here. That's good. So probability of, oh my god, doesn't like that too much. Okay, so probability of error. What's probability of error for the uncoded case? It's q of 1 by sigma, right? Using the q function you get this very simple answer. So if you want to write it in terms of SNR, it's going to be q of what? Square root of SNR. Okay. If you want to write it in terms of EB over N naught, it's going to be q of square root of
EB by root of 2 EB by N naught, root 2 EB by N naught.
Okay.
Root of
Square root of 2 EB over N. Okay. So it's very common. So in fact you can even simulate the entire thing with the decoder also, right? So it's easy to simulate that, you get your answers. Okay. So now it's very common to present so to speak the performance of such a system using a curve like this. You are going to put probability of error on the y axis, and then you are going to put EB over N naught on the x axis, and it is also very common to put EB over N naught in the dB scale. So, what is the conversion from regular scale to the dB scale? 10 times log base 10 EB over N naught. Okay. So, this is the conversion. So, you maybe start with 0 dB, 1 dB, 2 dB, 3 dB, so on. Okay. All right. And then you compute probability of error for each point on the x axis you want, and then you can make a plot, and the plot will look something like this. Okay. So, it will go off like this and it will come down here, and if you have something like 10 power minus 6 here. Okay, and it is also very common to have the x axis in log scale, the y axis in log scale, I am sorry. So, if this would be like 10 power 0, then you will have 10 power minus 1, 10 power minus 2, so on till maybe the last line here is 10 power minus 6. Where will 0 be on the y axis? Yeah, can't really go all the way to 0, okay, so you have to keep on going. So, it is a problem with the log scale, but it works to our advantage in some case. So, it turns out if you do the computation, you will see with Bpsk 1 and all that, this will hit around 10.5 dB if I am not wrong. Okay, so this is a good number to remember, 10.5 dB EB over N naught for the uncoded system gives you 10 power minus 6 probability of error. Okay. So, once again let me remind you how to simulate it. Suppose I fix my EB over N naught as 3 dB. Okay, how do I simulate this whole system? So, you have to compute from 3 dB, you have to compute sigma, right. Bpsk ES has been fixed at plus 1 minus 1, you have to compute sigma. Okay, for that it is a very simple formula, right. So, you go back to that formula and you compute sigma, and then you know how to simulate the whole system, right. You run the so as many bits as necessary. Suppose for 3, I do not know this exact number, so maybe this is some say roughly of the order of 10 power minus 2, okay. Then how many bits will you simulate? Yeah, you need at least some 10 power 4 bits. Okay, why is that? A good statistic to remember is if you are accounting for some event, at least that event should happen at least 100 times before you can be sure. Okay, well when I say when an event, either that event or its complement, it should happen at least some 100 times. So, every possibility should happen 100 times. Okay, you could have had an error, you could not have had an error. Usually error is much less likely, right. So, you have to simulate till you get at least some 100 errors. Why 100? Just accept it, 100 is a good number. Okay. So, if you have a probability of 10 power minus 2, you want 100 errors, you have to simulate some 10 power 4 blocks. So, for 10 power 4 bits, you will get roughly 10 power minus 2. Okay. So, this is quite important because many simulations you do this thing is involved. Okay. So, you get the answer. Is it okay? So, but you can also theoretically plot this curve, because you know the exact expression q of 1 by sigma, and that is related to the ERFC function. And when I say theoretically, I mean most programs like MATLAB will have inbuilt functions for giving you ERFC. Okay, so, you can plot it also without doing the simulation, you can check. Okay, so, this is a good thing to do. If you have not done it before, you should do it at least once during your stay here, I think. So, it is a good idea. Okay, now what happens in the coded system? That is what is more interesting to us. Okay, so. Oh man, this is really interesting. Oh, I think my this thing is different, that's why. Okay, so if you do coded, then several things change. First of all, you have k bits. Okay, these k bits are getting converted by the code nk code to n bits. And then these n bits are going through Bpsk, you get n symbols. Okay, so, if you want to compute energy per bit, okay, right. So, if you have Es as your energy per symbol, n times Es is the total energy that is coming out here. You divide that by k, this gives you the energy per bit. Okay. So, in other words, if the rate R is k over n, EB is Es divided by R. Okay. Now, in the uncoded case, what is R? R is equal to 1, so EB equals Es, so you are doing fine. Okay. In the coded case, R will be less than 1, so for the same Es, you will have a larger EB. Okay. So, and that is fair, okay, and you are making it fair. Okay. The energy per bit increases when you do coding for the same Es. Okay. Okay. So, now I mean I am not drawing the receiver side, I am just drawing the transmitter side, that is enough. Noise energy is simply sigma squared, which is n naught by 2. So, now if you define SNR is simply Es by sigma square, nothing changes. On the other hand, if you convert it into EB over n naught, you are going to get what? R times EB divided by n naught by 2. So, the general relationship you get is EB by n naught equals SNR by 2R. Okay. So, this is a good relationship to keep in mind. Okay, SNR by 2R. Okay. If you do Bpsk with Es equals 1, right, SNR is simply 1 by sigma square. So, for Bpsk this becomes 1 by 2R sigma squared. Okay. So, this is again a good formula to remember, 1 by 2R sigma squared, okay, for Bpsk WGN, that is the EB over n naught. Okay. All right. So, in most cases when you do coded modulation, you will not be able to get analytical expressions for the probability of error. Okay. First of all, there will be two different probabilities of error. So, let me also talk about that. So, suppose this goes through a channel, a noise is getting added, and then you do a decoder. Okay. So, if your message is if your code word is C, you get some kind of C cap here. Okay. Right. So, you can talk about frame error rate, what is called as FER, frame error rate or block error rate. Okay, I think FER is a bit more common, block error rate is also common. This is basically probability that C hat is not equal to C. Another thing you can talk about is what is known as BER, which is bit error rate. Okay, you can see why people prefer frame error rate to block error rate. Why? You get the same abbreviation if you do bit error rate or block error rate. Okay, on the other hand, if you say frame error rate, you get a different abbreviation and it is equally nice. Okay, well, it was meant to be a joke. I think people are looking at me very seriously. It is not a serious answer, you know. So bit error rate is probability that, let us say, Ci hat is not equal to Ci. Okay, and usually irrespective of I, for most codes this will be roughly the same, and in case if it is different for each I, you have to take the average of all of that. Okay. So, that is the understanding, but I will write it simply as Ci hat not equal to Ci. It is very unlikely that you get much lower probability, actually maybe it can happen, but usually it is the average bit probability of error. Okay. So, now how do you simulate this? You can simulate this, it is not very hard, right. So, you generate k random bits, do your encoder, get your n bits of the code word, send it through Bpsk, send it through noise, run your decoder. You have to now write code for the decoder, right. If it is optimal decoder, it is going to be very hard to write the code, but you can imagine, at least theoretically it is possible. You can write the code, you get your C hat, okay, and then what do you do in your simulation? You compare the C that was transmitted with the C hat that was received. If it is not equal, you have made one frame error or block error, okay, right. If it is not equal, you can also compare bit by bit and compute the total number of bit errors you made. Okay. So, at the end of say so many runs of this simulation, you will have a total number of frame errors which you will divide by the number of runs, and then you will have total number of bit errors which you will divide by number of runs and then divide by the n also. That will give you the final bit error rate. Okay. So usually what people do sometimes is important because it can make some difference in practice. Instead of computing errors over coded bits, they will compute error over only message bits. Okay. If it is systematic encoding, just take the message bits. Okay. So that is also done commonly. Okay. So for both frame error and bit error, you only count for the message bits alone. Okay. So if you make some mistakes in the parity bit, who cares, it does not matter, rest of the block can go through, alright. So that is how you simulate, and it is like I said, it is very important that you run simulations today, because any decoder you run or any modifications you do or any intelligent algorithm or code you come up with, it is very unlikely that given the complexities of soft decoding you might also have a very nice analysis for it. Okay. So you will have to run the algorithms to be able to do it. So today if you want to work in coding, you should be good in programming also. Okay. So the word coding now can be used in multiple ways and to mean the same thing or maybe different. Okay. Okay, so hopefully this is clear. So what you should do then is, okay, so now the idea is what is coding gain, right? So let me just capture this and then I will take it elsewhere and then we will talk about coding gain. Okay. So let us see, so I will remove all these other things that I do not need. Okay. So remember this is your uncoded plot. So usually you can go to MATLAB, click on add text and add uncoded there, show that that is uncoded, okay, or you put a legend for instance, you can do one of those things, and then what do? You run your simulation for the coded case and hopefully you get some line which looks like this. Okay, so this is a very typical kind of performance you would get. So this is coded. Okay, remember what is different in the uncoded and coded case? The definition of EB by N0 is different. Okay, so for the EB by N0 of 3 dB, you will get a certain sigma for the uncoded case. The sigma you will get for the coded case will be different. In fact, it will be larger. Okay, a rate is less than 1 means the sigma you get for the coded case will be larger. Okay, so that is the way to do a fair comparison. Okay, why should the sigma for the coded case be larger? Because you are spending more energy at the transmitter to send all the extra symbols, so you have to assume kind of a larger thing. Okay, so you can think of the computation. So remember what is this? This is equal to well not in dB, but let me write the other thing. This is equal to 1 by 2 r sigma squared. Okay, for the uncoded case r is equal to 1. For the coded case r is less than 1, some number that you have. So for the same EB over N0, if you are plotting in the same axis, the sigma value will change depending on whether or not you have coding. Okay, so that is something slightly subtle. Another way to think about it is, suppose I keep my okay, this is another digital communication way of thinking about it. So sometimes what you do is you increase the clock rate when you do coding, right? You know what I mean by clock rate. So you put in more symbols for the given time. So what will happen when you do that is your frequency of that you are using increases, so you will let in more noise. So literally that is kind of captured by this increase in noise for the same EB over N0. Okay, so that is the way, that is another way of thinking about it. Anyway, it does not matter. So now comes the definition of coding gain, which is usually fixed at some particular probability of error. Okay, so you have to fix whether it is bit, usually it is in bit error rate. Okay, so let us say this is bit error rate. Okay, and usually 10 power minus 6 is a conventional bit error rate at which people measure coding gain. Okay, so they will look at where this crosses the axis and where the uncoded line crosses the axis, and you draw some kind of a line there with double arrows, and the length of that line is your coding gain. Okay, and it is real fair coding gain, there is no unfairness in the comparison, right. You will so to speak, you will see this gain in practice. Okay, if you are getting a certain 10 power minus 6 bit error rate for a certain power at the transmitter, if this coding gain happens to be, let us say, some 6 dB, you can reduce that power by 6 dB, do coding and still recover that exact same probability of error. Okay, so that is what it means. It is very real number. It is not some number that you have cooked up from nowhere. Okay, so it gives you a 6 dB power reduction if this coding gain is 6 dB. Okay, so in practice, this is how you evaluate coding gain these days. It is mostly simulation based. It is very hard to do analysis. Only for the Reed-Solomon BCH code kind of things you can do analysis. It is very difficult to do analysis in practice for these new codes that are out there. Okay, I haven't really described what these new codes are, but this is how we will be justifying it. Okay, so hopefully this is clear. This is quite important. If at all you are doing any coding in your life after this, you will be producing curves like this. Okay, well, maybe there are other types which where you don't produce codes like this, but usually if you work on codes, you are looking at some curve like this. Okay, so the other question to remember, another point to remember is, suppose you fix a particular rate and you say I want to use more and more powerful codes, but for a particular rate, let us say rate equals half. Okay, you would think if you use more and more powerful codes, what will happen to the coded curve? It will go to the left. You want it to go to the left, but it turns out it cannot go more left than a certain point. Okay, so it will go up to a certain point, which you can call as a capacity achieving SNR, Reb over N naught. Beyond that, it cannot go to the left. Okay, so that is a very standard result in information theory. Once again, we won't go into that, and usually for rate equal to half and all that, that line will come somewhere here. Okay, somewhere between 0 and 1. Let us say for rate half, it is about 0.6 dB or something. Okay, so this is the capacity line. So what this capacity means is, for a fixed rate R, there is a certain maximum coding gain that is feasible. Whatever you do, you cannot get better than that coding gain. Okay, and that is a very strongly analytical, clearly well established result. Okay, so it is not some heuristic or anything. Okay, so it is a very mathematically clearly proven result. If you take a course in information theory, you will learn more about it. In fact, a course is being offered next semester, that same information theory, or you may not know about this. So anyway, it is good information for you. So it is being offered next semester, so you can take that and you will learn how to compute this capacity. Okay, so it is a very interesting idea. So now, how do you measure coding schemes? One way is to say I get so much coding gain, but that is just a number, right? How do I know I am doing really well? How far are you from the left? And that is called gap to capacity. Okay. Okay, and that is also a very nice absolute way of measuring how good your code is. Okay, you might have a very fancy idea by which you develop a fantastic code, but if your gap to capacity is 3 dB, then you are not doing that good. Okay, if somebody else has a code which has a gap to capacity of 0.1 dB, then they are doing way better than you. It does not matter what you do, right? It is an absolute measure in terms of the best that is possible. Okay, so both these things are equally important in practice. Okay, for a long time gap to capacity was nobody worried about it, but today when you design codes, your gap to capacity should go very small. Okay, so people have really come up with very smart codes which have very low gap to capacity. Okay, so those are the codes that we will be studying in the rest of the class. Okay. Okay. So at this point, it is good to pause and look at our classical algebraic codes. Okay, the BCH and Reed-Solomon codes, which have fantastic structural properties, they have strong algebraic roots, they are very nice codes. How well do they do here? Right, that is an important question to ask. Where will they be in this curve? Okay, what is their coding gain? What is their gap to capacity? That is an important question to ask. Okay, so for that, I am going to pull out two different curves that I already have. The first one is a 7-4 Hamming code. Okay, so here is that curve. Can you see that? Okay, so there are three different curves here. Hopefully, all of them are visible to you. Okay, one is the black curve, which is marked in the legend as what? Uncoded. So I think what I should do is I should probably call it from journal, so then I can write some comments on it. Where is my journal? I am sorry. Okay. Okay, so I think I should insert from here. Then I think it's nicer to see. I can add some comments on it and okay. Okay, so this curve, so this black curve here is the uncoded curve, and you can see, like I said, 10 power minus 6 roughly around 10.5 dB. Okay. And then this is, remember, this is the 7/4 Hamming code. Okay. The red curve is the hard decision. So, this is syndrome decoding, hard decision. Okay. So, what do you do when you do hard decision? You first slice and then you run a syndrome decoder, and then the green curve is a soft ML, it is a soft ML decoder. Is that okay? So, how well is the 7/4 Hamming code doing in terms of coding gain? Okay, the hard decoder is doing quite bad, you know. So, even at 6 dB, it is doing worse than the uncoded case. Okay, only around 9 dB or 10 dB or so you start seeing some gains because of the hard decoding. Okay, but the soft decoder is doing quite all right. So, even at let us say 10 power, so if you measure at, let us say 10 power minus 4 bit error rate, roughly about, how much is this distance? So, let us say roughly about 1 dB. Okay, at 10 power minus 4. No, I mean this is going to cross somewhere here, right? So, I think say roughly about 1 dB. So, you get 1 dB of coding gain from the Hamming code, and the capacity is going to be somewhere close to 0, and the gap is about 7 dB or so. So, you are far away from the capacity. 7 dB is a lot. I mean, you might think, what is 1 dB? I do not know if you know, maybe you may not have worked with so much circuits or anything. So, it turns out most communication systems at the very front end, they have these power amplifiers, what are called power amplifiers. These are analog electronic devices, okay, and they are very, very expensive. Okay, the reason why they are expensive is you want linearity and in phase and everything in your communication, right? You are doing QAM, you want phase and all to be preserved, you can't have something which is non-linear. Okay, so all that you want, and you want also high power, because it has to go over large distance, and that happens to be a very expensive component, and if you can reduce the power of that by 1 dB, the price will go down by several tens of thousands of dollars. You can imagine that. So, it's a big reduction in price. Okay, so coding gain really buys you a lot of things. 1 dB is not bad, but maybe if you are giving up on 7 dB, maybe you should think about it. Maybe there is something more I can do to gain from the 7 dB loss, right? So, think about various applications. For instance, if you think of a satellite that is way out there next to Mars, it is getting all its energy from the sun, you know, I mean, it does not get too much energy Mars. So, you can't keep spending all kinds of energy, right? If you have 7 dB to gain, 7 dB is a big difference. Okay, maybe you can go from Mars all the way to Jupiter and still communicate. Right? So, that is the way to think about these things. I mean, these are used, I mean, codes are used by NASA a lot, and NASA is a big what do you say, big spender of money for designing good codes. Anyway, so this is the Hamming code. Okay, so what about other codes? Let us say maybe, so what would you say, is it good, bad, or ugly, or not bad? So, if complexity is a major limitation, 7/4 is really less, right? I mean, if you think of what you can do with today's VLSI, it's really less. Okay, so maybe if you go to longer block lengths, you can do something better. Okay, so 7/4 is really low, and maybe you can even show that for this block length and this rate, you can't do any better than this. Okay, so it's really low block length, right? 7/4 you can't do much. That capacity that I drew is valid only when block length becomes very large. Okay, so in fact, it's tended to infinity to prove that result. Okay, so you can get to those values only for long block lengths. So, there is no point in comparing a 7/4 Hamming code with something infinite and say, okay, I have a gap. Of course, you will have a gap. Okay, so you can't do anything better than that. Okay, so let us take longer length codes. Let us say some Reed-Solomon codes. So, I do not know, will this be able to insert PDF files? See, it is not able to insert PDF files. I am sorry. Oh, I can open it and then cut and paste from there, is it? Okay. This is what I do. and then I can copy it onto that. Okay, so that is not bad. So this is what happens for block error rate versus EB over N naught for some BCH and Reed-Solomon codes. Okay, so I believe the solid line is I do have two lines. Okay, so solid line is the Reed-Solomon code, the dotted line is the BCH code, and then this other curve is the uncoded picture. Okay, so what have I done here? I have done same minimum distance for BCH and Reed-Solomon. This is over GF 256. So I have taken a GF 2 power 12 whatever BCH code, a larger BCH code. So BCH code will be slightly better than the Reed-Solomon code. We know that that's true, right? The minimum distance is slightly better, so it will be better. And these are actually hard decision decoders. Okay, so you do hard decision decoding. Hard decision decoders, no soft decision. Okay, so you can see it crosses 10 power minus 6 at around 6 dB, right? 5.5 to 6.5 dB, right? And look at the rate of the code. So this has got a minimum distance of 65. This has got a minimum distance of 129. Okay, so this is a rate half code. This is a rate 3/4 code roughly. Okay, so those are the things I have picked. And still there is a gap to capacity. The gap to capacity is about 5 dB or so for rate half and all that. It's a large gap, and it also gives you a coding gain. The coding gain is also large. I have gone to a larger block length. I have used a code. It gives you some coding gain, even with hard decision, right? So that's something that's valuable, right? Hard decision decoders are much simpler to implement. The PGZ decoder is not too complicated. Its complexity is not exponential in K, right? It only depends on the error correcting capability. So it can be implemented, and you get decent coding gain. But the only drawback of these codes definitely is this gap. Okay. Can you do anything about this gap? Is there what needs to be done for this gap? So clearly soft decision decoding has to be used in this gap. Okay, so otherwise you're not going to do much better. As long as you stick yourself to hard decision decoding, this kind of gap will always be there. So you have to do some form of soft decision decoding to overcome this gap. Okay, so that's something that's important. Okay, so the question was, should I say anything more about capacity, but not in this course. It just takes longer to explain.
For big block lengths, how close would be?
Okay, so the question is, if I were to implement ML, soft ML decoder for these Reed-Solomon BCH codes, how far to the left can it go? Actually, I don't know the answer to the question, to be very frank, but there are some results on ML decoding of Reed-Solomon codes, but not for these kind of block lengths. I think it's difficult to analyze. There are some soft decoders for Reed-Solomon codes which give you about 2 dB or so additional coding gain, maybe maximum 2 dB, but not at these kind of, maybe at these kind of rates you will get better, right? But nobody has shown that it can get to 1 or something. There is no such result that Reed-Solomon codes you can run some decoder, even ultra theoretical. Let's say, some decoder is very complex, but somehow somebody has analyzed it and shown that it can. Of course, if it's so complex, you can't simulate, right? You have to analyze. So nobody has done that. Nobody has shown that it's close to 1 or something. But for other codes, people have shown even simulation results very close to capacity. Okay. In fact, there is a paper which says there is an LDPC code, low density Parity-Check code, which gets to 10 power minus 6, 0.01 dB away from capacity. So 0.01 dB rate half. Okay, so 0.01 dB would be almost there. In this picture, you can't see it. So the question to ask is there anything else left to do in coding? Right? There's capacity, and you've achieved capacity. What more? Try to push the capacity. Yeah, there are some limitations to that code also. Of course, you can show it, but that's something to think about. Okay, so So see, again, I don't know the answer to that question. If you were to do ML decoding for these BCH codes, can you push it to the left? I think it's, maybe there are some theoretical answers, but I don't know if there are any practical answers. But definitely any implementation of soft decoders is very hard for BCH codes and Reed-Solomon codes, that much is true. It's very hard, and there is no suboptimal. The problem is there is no easy way to iteratively improve a suboptimal answer. So you saw in the bitwise MAP, the main motivation is you have one answer immediately, then the next answer you get from the next parity check, next answer improvement you get from the next parity check, right? As long as you keep it independent, you are okay. But in Reed-Solomon codes, you will see the dual has all kinds of weight. When dual also has a large weight, it turns out dual of MDS codes are also MDS, you can show that. So they are also large weight, so you will only have large weight vectors in the dual, and what do? You can't do suboptimal with that the way we do for the other codes. So that is one problem. So you have to overcome that in smart algebraic ways, and it is possible. There are soft decoders, but they give about 2 dB or so, not too much more than that.
Steep behavior.
Why does it show the
Steep.
Okay, the fall, why is it so steep? Yeah, it's usually like that. It's like that. You can show that the fall will be like that. You can do the computation in the expression. So these are actually theoretical curves. These are not simulated. I've just assumed bounded distance decoding. Okay, if you do the computation for bounded distance decoding, all errors up to a certain point can be corrected, right? That itself will give you a steep fall like this. What is less than 4? I'm sorry?
Is it 0.5 bit?
Which one?
For BCH.
I'm confused. What is the question? Oh, less than about 4.5 dB, it's worse than uncoded is what you're saying. Yeah, that will always happen for hard decision decoders. I'm sorry?
That's because the sigma is higher because of the EB by N naught equation.
Yeah, I mean hard decision decoders will have this problem. They'll always be, they'll cross the uncoded curve somewhere. If you do soft decision, then you'll see it'll be slightly better. It will do something, it will follow the uncoded thing and then it will come down like that. There is also block error rate, no? So this is slightly different. If you compute bit error rate, something more will happen. Something very different will happen. Block error rate also is a misleading reason why this weird curve is showing up. Okay, bit error rate will be slightly different.
How do you compute bit error rate for a bounded distance decoding? Because
You can't
sometimes
analytically compute. It's very difficult. So question was, that's why I have computed block error rate. Okay, block error rate is very easy to compute. Bit error rate is harder to compute in a bounded distance decoder. There are methods, you can do approximate computation and that will look much better here. It will come out to be a little bit better, but block error rate is a very easy expression. So I can evaluate it very nicely. At least the approximation for block error rate is very easy. Any other question? These curves? Okay, so at this point we have kind of done some general background on soft decoding, and then we have seen how to measure, how to do some suboptimal, some general ideas on how to do suboptimal soft decoders, and then how these classical codes do when you look at them from a coded modulation point of view. What is the coding gain that they provide? How far are they from capacity? Okay, what we are going to see from next class is codes which have very good suboptimal soft decoders that can get close to capacity. Okay, there are two types of codes like that which are very popular today. One is this low density parity check code, which is what we will see immediately. And after that we will see these turbo codes, which will come up a little bit later. Okay, so we will stop here.